Albert Einstein may have explained in the language of physics what people throughout history have been trying to explain using the language of metaphysics, i.e., time dilation. What is relativity? One may say that it is a way of looking at events, but it is perhaps better described as a way of understanding other events. It is easy to understand and measure our own coordinate system, but it is relativity that allows us to now understand other systems. Einstein showed, using a series of mathematical expressions, how the universe appears from another perspective. Here's how it works.
When two Alright, you want me to just keep going?
Is that something you can cut, or should we just back it up?
Jesus Christ! Keep going!
Okay. When two systems are in motion, whether it is uniform translation, such as is necessary for the special theory, or accelerated motion, which becomes okay according to the general theory, but not the same motion, an observer stationed on one will disagree with an observer stationed on the other about the space-time. Distance might be a wiser choice until we have a chance to discuss space-time traversed.
A series of equations called the Lorentz transformations can be used to predict the discrepancy in the observations of the observer riding with a system and an observer riding in another system. For instance, a spaceship passes a fueling station at, let's say, 7/8 the speed of light. A passenger on this traveling ship notices another ship parked while its captain is using the facility. The passenger thinks it is strange that the other ship, the same model, is only half the size of his, and the captain, were he unoccupied, would have made the same observation about the traveling ship.
In their own systems, both ships retain their original sizes, but when observed from another system moving at sufficient speed in relation to them, the ships appear to be only half their original sizes. So do all events in the other systems. Neither is it only the measurement in feet of the other system, it is also the measurement of time.
Now, in this example of a ship passing a
fueling station, the passenger riding on the traveling ship did not wonder whether he was passing the station or the station was passing him. He was perhaps a slave to convention, but suppose he wasn't. Suppose instead that he claimed to be sitting very comfortably in his ship when all of a sudden a fueling station came zipping by him at that dangerous. Can the captain prove anything to the contrary? Is there any argument except convention, which says fueling stations do not travel past ships? No, not even my mom says that. This is why observers in both systems observe the same phenomenon. For, according to relativity, what is true for one system must also be true for another, indeed, every other.
The Lorentz transformations have their basis in the traditional Galilean transformation, i.e., capital W equals W plus V, where the big picture, or total velocity, capital W, of an event is equal to the simple sum of its parts, or the combined velocities of the events taking place within it. That's not too clear, is it? Okay, suppose the passenger on the traveling ship to be walking stern to bow with velocity W, and the ship to be moving with velocity V. From the station, according to Galilean physics, the velocity of the man, W, will be the sum, W plus V.
Due to some experiments by a Dutch physicist, de Sitter, and some work done with electromagnetics, it became evident that the propagation of light had to be a constant c, nor could anything travel faster than that speed. Now, look at the ship problem again, and suppose the man to be walking at greater than 1/8 the speed of light, and the ship to be moving at its original 7/8 the speed of light. Yikes!
Yikes!
It is granted the Lobachevskian geometry and the Gaussian coordinates, as well as the theories of Relativity may only apply to extraordinary events. Lobachevsky deals with very large, even infinite space and distances. And Einstein shows minimal distance and time alteration, many times undetectable by the human eye at velocities of up to half the speed of light. Einstein's theories could not be immediately proven, for they came out of what some call intuition. But it was more than guesswork that this word implies. Einstein rather saw a pattern in the events of the world, in the functions of the world, into the world itself, and the universe as a whole. This pattern is evident in Einstein's repeated calling for symmetry into physics. Whatever is true for one event observer must also be true for not only one other, but for all others. This pattern is the basis of relativity.
This pattern is the basis of relativity.
This pattern is the basis of relativity. The reason Euclidean geometry and the Galilean coordinate systems do not work for all reality is because there is no all reality. The universe is constantly changing. What were plane surfaces at one moment waver and become hyperbolic or conic. Lines, bends, and points float. This is the same effect for all geometry, not just Euclidean. Geometry takes shape the same way, indeed the exact same way, as space is defined by electromagnetic fields.
The electromagnetic fields shape the universe. When they move about, the universe's shape moves about as well. This is the cause of the non-rigidity of space. Can this be what causes the universal pulse? Does the energy the jazz musician feels while playing on a good night originate in these fields of electromagnetism? Is the universal pulse electromagnetic?
Very possibly, yes.
We can control the magnets here on Earth in very small spaces, compared with the universe of relativity. Therefore, we can control the pulse in very small amounts. Imagine, however, the effect of the moon passing the Earth, or the Earth passing the sun, or our solar system passing another. With these movements, space is redefined, not only constantly, but continuously. Therefore, Euclidean geometry can never be right for more than a moment. Triangles.
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 Triangles?
Triangles.
Triangles melt into other shapes.
Relativity compares events in two coordinate systems, much the same as if we were to compare the triangle at one space-time event to that of another.
So it is not difficult to imagine the slightest change in our spirit completely changing our universal perspective. It's still weird to think that the equations of Einstein's relativity might be involved, isn't it?
Now, for the grand finale, let the universal pulse be the third, or ideal observer, and the two drummers be the two events observed. And we will imagine measuring their rhythms in space-time coordinates. They, the two, observe and concentrate themselves, each on his or her relation to the universal pulse, and through the series of equations called the Lorentz transformations, the two synchronize and play as one.
They are simultaneous, if only for a moment.
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 Moment.